In 4.2, we're going to look at the first and second derivative and see what it tells us about the graph of a function. So the first thing we're going to talk about is when a function is increasing or decreasing. Notice in the two graphs below, as my x values get larger and larger and larger, the graph is going up. And that's what this first part says. It says it's an increasing function if, as your x values get larger, your y values also get larger. In the second graph, as my x values get larger, my y values are getting smaller and the graph is going down. So this is an example of a decreasing function. So our function is decreasing if the x's are getting larger but the y values are getting smaller. So here we have increasing and decreasing. So to help us find intervals where a function is increasing or decreasing, what we could use is this theorem 4.3. So this is a test to find the intervals of increasing and decreasing. And what this theorem says is if the first derivative is positive, then the function is increasing. If the first derivative is negative, then the function is decreasing. Now on this graph here, I'm going to first look at where the function has a zero derivative, and it looks like there's 3 places where the derivative is 0. I'm going to guesstimate that this is about, why don't we go with negative 3.2. And then we have 0 and 3. So that's where the derivative is 0. So that means on either side of those critical points, the derivative will either be negative or positive. So looking at negative infinity to negative 3.2, if I pick any point on this graph, the slope of the line, or the derivative at that point, is going to be negative. So since the derivative is negative, the function is going to be decreasing. So let me go ahead and list the intervals of decreasing. So far I have negative infinity to negative 3.2. And these are always parentheses because we don't include where the derivative is actually 0. Now if we go from negative 3.2 to 0, notice that if I compute the derivative at any point there, it's going to be positive. So that's where our function is increasing or going up. So negative 3.2 to 0, we have increasing. And then from 0 to 3, if I compute the derivative at any point, from x is 0 to x is 3, I see that the derivative would be negative, and our function is decreasing from 0 to 3. And these are x values. And in our last piece, greater than 3, the derivative is positive. So that would be where our function is increasing or going up from 3 to positive infinity. So let's say we don't have a graph to look at. But we could still use that theorem, because that theorem says figure out where the derivative is negative and positive, and that will tell you increasing or decreasing. So the first thing I want to do is compute the derivative. So if I compute the derivative of this function, it's going to be 3x squared plus 8x minus 3. First thing I'm going to do is figure out where the first derivative is 0. So if I set 3x squared plus 8x minus 3 equal to 0, I believe that's factorable. I think it's 3x minus 1, x plus 3. So when x is equal to 1/3, or x is equal to -3, that's where the derivative is 0. What I'm going to do is I'm going to look at a number line. And if I look at this function, it's a polynomial function. It's defined from negative to positive infinity, so that would be its domain. Now these are critical points where -3 comes first and then 1/3. So what I'm going to do is I'm going to find test points within these intervals. So from -infinity to -3, maybe I'll put in a -4 as a test point. From -3 to positive 1/3, 0 would be a good test point. And greater than 1/3, 1 would be a good test point. So what we're testing in is we're going to be putting these test points into the first derivative to see if the first derivative is negative or positive. Okay? So I need to figure out where the first derivative is 0 or undefined, find our critical points, and then do test points to figure out where it's negative or positive. So if I put in -4, I can see that the derivative here would be positive. If I put 0 into my first derivative, I get negative. And if I put 1 into the first derivative, I get positive. So what that tells me is that the function's going up and then down and then up. So it's going to be increasing from -infinity to -3. And then again, it's going to be increasing from 1/3 to positive infinity. The function's going to be decreasing on the interval from -3 to positive 1/3. So although this question did not ask us to find a local min or a local max, what I want you to notice here is that if the function goes from increasing to decreasing, what that tells us is that there's going to be a local max. If the function goes from decreasing to increasing, that tells us we're going to have a local min. And that brings us to our next theorem. Something else that the derivative can tell us is it could tell us where we have some extrema. Okay? So in theorem 4.4, we're going to look at some critical points. So that would be where the function is 0 or the first derivative is 0 or undefined. If the first derivative changes from positive to negative, then we have a local max. If the first derivative changes from negative to positive, we have a local minimum. If the derivative does not change sign, then there's no local extreme value. So let's look at this graph to see what that theorem is telling us. Okay? Again, when we're talking about critical points here, we're looking at where the first derivative is 0 or where the first derivative is undefined or does not exist. Now I'm going to go ahead and add arrows to the end of this and pretend like it goes on forever and ever. Okay, so at 2, and here between 2 and 3 somewhere, and at 4, these are my 3 critical points. From negative infinity to 2, if I were to compute the derivative here, it would be positive. And our graph is going up. From 2 to this next critical point, which is almost 3, the derivative is negative, and our graph is going down, it's decreasing. So notice that the derivative changed from positive to negative. That means that at 2, we're going to have a local max. Now, between our second critical point and 4, the derivative is positive. So it's gone from negative to positive. It's changed sign. So here we're going to have a local min. But notice that at 4, we're going from positive to, compute the derivative after 4, it's still positive. So in this case, at 4, there is no local min or max. So again, what that theorem is saying, that if the derivative changes sign from positive to negative, or negative to positive, then there's a local min or max. If it does not change sign, then there is no local min or max. So the next theorem we're going to look at is theorem 4.5. And what theorem 4.5 says, it says that if there is one local extreme value, then that is also the absolute extreme value. So a very simple example would be this parabola. Notice that we have one critical point at 0. The derivative goes from negative to positive. So we have a local min. But since there's only one local minimum value, what that means is that that's also an absolute minimum value. Okay? So one local extreme value means it's an absolute extreme value. In example 3, we don't have a graph, we just have the function, and we need to find all the local extrema. So the first thing I'm going to do is I'm going to find the first derivative. And then figure out where it's 0 or undefined, find critical points. And then I'm going to test to see if the derivative is positive or negative to find my local extreme values. So the first derivative is 5x to the 2/3 minus 4/3 x to the negative 1/3. Okay, now I'm supposed to figure out where this first derivative is undefined or where it's 0. So what I'm going to do is I'm going to set this equal to 0 first. And I notice that there's an x in both terms. So now you don't have to do it this way. But I'm just going to go ahead and factor out the common x, choosing the smallest exponent 1/3. So when I factor out x to the negative 1/3, what remains in parentheses is 5x minus 4/3. And that's equal to 0. setting each factor to 0, I have x to the negative 1/3 is equal to 0, and 5x minus 4/3 equal to 0. Now x to the negative 1/3, remember that that's 1 over x to the positive 1/3. And that's never equal to 0. However, if x is 0, then it's undefined. So x equal to 0 is a critical point, because that's where my derivative is undefined. Now solving 5x minus 4/3 equal to 0 gives me 5x equal to 4/3. And then when I divide by 5, I'm going to get x is equal to 4 over 15. So I have these two critical points that I'm going to use to break up my number line. And then I'll test on either side of those critical points to see if the derivative is negative or positive. So remember, I'm testing into my derivative, my first derivative. I have 0 and 4 over 15. So I think a good test point would be -1. And then from 0 to 4 over 15, well, 3 over 15 is in there, which would be 1/5. And then greater than 4 over 15, 1. I'll use that test point. When I put in -1 into my derivative, it becomes positive. If I put in a positive 1/5, the derivative will be negative. And if I put in a positive 1, the derivative is positive. So what I notice is that the derivative goes up, down, and up. So since the derivative did change signs, that tells me that there's going to be a local max at 0 and a local min at 4 over 15. However, since there was not one change of sign, we had two sign changes. There's no absolute extreme values. So if there's one sign change, then there's an absolute extreme value. But we had two sign changes. And that makes sense because you think about this function f, not the derivative, the function itself. It's defined for all real numbers, which means if I were to graph this function, it would just keep going up, 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 and down, down, down. So I could see that this would not have an absolute min or an absolute max. It just has a local max and a local min. So we have a local max at x is equal to 0. So if I put 0 into my function, then I get a y value of 0. So it's a local max at x is equal to 0, but the local max is 0. And we have a local min, and it happens when x is equal to 4 over 15. But the local min itself, now I have to put this in my calculator because I don't want to do this by hand, put in 4 over 15. And when I do that, I have a local min of about negative 0.5. Okay, and it happens when x is equal to 4 over 15. So something I did want to point out is the shape of this graph. If a graph opens downward. We say that the graph is concave down. If a graph opens upward, we say that the graph is concave up. So another thing that a derivative can tell us is the actual shape of the graph. Not just if there's local min-max, absolute min-max, and increasing, decreasing. It can also tell us the shape of the graph, if it's concave up or if it's concave down. So this would be the definition of concavity. And we're actually not going to use this definition, but we should talk about the definition. When we figure out concavity, we're going to do something else. So when we talk about concavity, whether a graph is concave up or down, if the first derivative is increasing, now this doesn't say the first derivative is positive, it just says, is the first derivative getting larger and larger? Then it's concave up. If the first derivative is decreasing, if the first derivative is getting smaller and smaller, then we have concave down. If the function changes concavity, then we call that an inflection point. So if it goes from concave up to concave down, or concave down to concave up, that's an inflection point. When we look at this graph here, I can see that at C and at D and at E and at G, these are all the critical points. This is where my derivative is 0, or the derivative is undefined. Now notice that from negative infinity, and we'll assume that this graph just keeps going. From negative infinity to this point C, if I compute the derivative, it's positive. But notice that the derivative is actually getting smaller. It's going to be positive, but it's getting smaller and smaller. It's decreasing until at C the derivative is actually 0. So it goes from positive to 0. The derivative itself is decreasing. So that means that our graph is concave down. It's opening down. And then from this point C to 0, again what's happening is our derivative is still getting smaller and smaller. It happens to be positive from C to 0, but it's still becoming smaller and smaller values. So that's where it's still going to be concave down. Now from 0 to this next critical value, D, I notice that the derivative itself is negative at every point. But it's actually getting larger and larger. It goes from negative values to 0. So the derivative is increasing, and that means that our function is concave up. So we can keep doing this, looking at the derivative and testing to see if the derivative increases or decreases, but it's very tedious and it's kind of hard to tell. So from 0 to E, our function is concave up. Now notice at E, this is a critical point. This is where the derivative is undefined. But notice that the concavity did not change. It's still concave up. So what that means is that this is not an inflection point at E. So an inflection point happens when the concavity changes from up to down or down to up. However, at 0, this is an inflection point because my graph changed from concave down to concave up. So the test for concavity is very difficult if we use the first derivative. So what we usually use is theorem 4.6, the test for concavity. And it's a very simple test. So we're going to assume that our second derivative exists. If the second derivative is positive, then it's concave up. If the second derivative is negative, concave down. If the second derivative is 0 and we have a sign change, then it's an inflection point. So very simple. All we have to do is find the second derivative. In example 4, we're going to test for concavity, and then we'll identify any inflection points. So to test for concavity, I need the second derivative. My first derivative is going to be 6x squared minus 12x minus 3. The second derivative is going to be 12x minus 12. So the first thing I want to do is figure out where the second derivative is 0. So this is going to be 0 when x is equal to 1. That's going to break up my number line. And I just have one critical point here. So remember what we're doing is we're putting in values into our second derivative to see if it's concave up or concave down. A good test point would be 0, and 2 would be another good point. If I put 0 into the second derivative for x, then it's negative. If I put in 2, the second derivative is positive. So what that tells me is if the second derivative is negative, then I have concave down. If the second derivative is positive, we have concave up. So concave down, the interval would be from negative infinity to 1. And then we have concave up from 1 to positive infinity. Now notice that the sign changed from negative to positive. So if the sign changes, then it's an inflection point. So the inflection point is a point where the x value is 1. So if I put 1 into my function, remember we're trying to find the point on the graph where there's an inflection point. So when I put 1 into the original function, I get back 0. So we use the first derivative to find increasing, decreasing, and we use the second derivative to find concavity. We've also used the first derivative to find our local extrema and absolute extrema, if there's just one local extrema. But we can also use the second derivative to test for local extrema as well. So let's look at theorem 4.7. Let's say the first derivative is equal to 0. If the second derivative is positive, then we have a local minimum. If the second derivative is negative, It's a local maximum. And if the second derivative is 0, then unfortunately we can't use this test. It's inconclusive. So for example, let's look at this graph. We have these 2 points where the derivative is 0. So notice that the concavity is down. So since the concavity is down, the second derivative is negative. So this becomes a local max. Now in the second part, concavity is up. So if the concavity is up, then the second derivative is positive. So second derivative positive, first derivative 0. This is going to be a local min. So we have a local max and a local min. We're going to go ahead and use that second derivative test in example 5 to locate any extreme values. So the first thing I want to do is compute the first derivative and figure out where the first derivative is 0. And then I'll plug those values into the second derivative. Notice that we're not looking at where the first derivative is undefined, because then we wouldn't be able to plug those values into the second derivative. If the first derivative is undefined, then when we compute the second derivative, it'll be undefined as well. This is going to be 4x to the third minus 12x squared plus 8x. Now I want to figure out where this is 0, so I'm going to go ahead and set the first derivative equal to 0. And then I'm going to see if it factors. I want to avoid using a calculator as much as possible. Oftentimes a calculator will give you an approximate value. It won't give you an exact value. So I can see I can factor out a 4x. And what remains would be x squared minus 3x plus 2. And that factors into minus 2 minus 1. So x minus 2, x minus 1. So setting these equal to 0, I have x is equal to 0, x is equal to 2, and x is equal to 1. So remember, these are the values where my first derivative is equal to 0. So now by the theorem, I have to take all 3 values and test them in my second derivative. So now let's go ahead and compute the second derivative. The second derivative is going to be 12x squared minus 24x plus 8. The second derivative evaluated at that first point 0, that gives me 8, which is greater than 0. So this is a local minimum. Okay, so if the second derivative is positive, then it's a local min. I'm going to compute the second derivative at 2. And it looks like that's also going to be 8. Since it's greater than 0, that would also be a local minimum point. And then the second derivative at 1, negative 4. So since that's less than 0, or negative, that tells me it's a local max. So that's it for this section 4.2. In the next section, 4.3, we're going to be putting all of these concepts together to graph our functions.